Good afternoon. So today we will talk about a couple of topics related to calculus with parametric curves. The idea is to use some of the calculus tools we already know, like taking the derivative, finding the tangent line, finding the arc length of a curve, without the need to revert back to Cartesian coordinates. So how do we do these useful things, taking the derivative, tangent line, and the arc length, directly with parametric curves? So basically the answer given in terms of the parameter t, or theta if you talk about polar coordinates later. So let's start already with an example. Well, before I talk about an example, we're going to figure out first of all how we take the derivative, because that's obviously at the root of everything, right? So we need to figure out how to compute the derivative using parametric equations. And then we're going to talk about finding the tangent line to a curve or the arc length. So taking the derivative, as you might expect, is not much different than in the way you did it before, with one caveat, in the sense that it's via the parameter t. So you basically use the chain rule. Well, I mean, the formula for taking the derivative of a parametric curve is based on a chain rule formula. So the idea is this: let's say you have a parametric curve given by f of t and g of t, right, for the x and the y coordinate. And although you have it that way, I mean, although you have the parametric curve, let's say you still want to compute the change in y with respect to the change in x. So let's say you still want to know what dy dx is, even though the answer in this case is going to be in terms of t, in terms of the parameter t. So you won't lose the need of finding the change of y with respect to the change of x, which is the meaning of the derivative in the traditional sense. But now you don't have y as a function of x, nor x as a function of y, right? Each of them, x and y, are functions of the parameter t, yet you still want to know or to compute, even though you may have that answer in terms of t, you still want to compute the dy dx, right? The derivative of y with respect to x. Because if you think about it, let's say you have a motion in the plane like this given by this parametric curve. You may still want to know, for instance, the equation of the tangent line. And the equation of the tangent line requires the slope. And the slope of that tangent line is still dy dx at that point. So the slope is still given by dy dx, or the derivative of y with respect to x, at the point in question. But again, we don't have y as a function of x, nor x as a function of y. So how do we compute this quantity in terms of the parameter t? Well, the answer is the chain rule. It's as simple as that. Notice that if I look at dy dt, I can view y as a function of x, which in turn is a function of t. So then I can relate dy dx with the derivatives of y with respect to t and x with respect to t, right? So if I view y as a function of x first and then as x as a function of t, then dy dt via the chain rule can be written as dy dx times dx dt. So again, this is nothing new. This is simply the chain rule. And we use it because obviously we know how to compute these guys, dy dt and dx dt, because we have them as functions of t already. So from this equality, provided that dx dt is not equal to 0, I can get that dy dx, the derivative of y with respect to x, is dy dt over dx dt, provided that dx dt is not equal to 0. So that's the formula for taking the derivative of y with respect to x in a parametric curve. It's simply y prime of t over x prime of t. So let me write it down again as a formula here to have it in front of you. So dy dt, you can write it as a fraction if you want, over dx dt. Or in using my notation above, that's f prime of t over g prime of t. Or you can even write it y prime of t over x prime of t, right? I mean, because again, y and x are functions of t via that parameter t. So let's do a quick example. And then one thing that is sometimes kind of misleading or confusing to students is, for example, if you need to take the second derivative. So I'll talk about that in a minute. Let's just do the dy dx first. So let's take an example. So suppose I have x equal to t squared plus 1 and y equals t squared plus t. And then according to this formula, then dy dx is going to be dy dt over dx dt. And our dy dt is 2t plus 1 over dx dt, which is 2t. So in terms of t, dy dx is equal to 2t plus 1 over 2t, which is valid if t is not equal to 0, right? Because you can have division by 0. So I have to actually stop for a second because I just ran out of ink. All right, so we could simplify this further if we want. You could say that dy dx is equal to 1 plus 1 over 2t. All right, so what if we want the second derivative? So what about d2y dx squared? So what if I want the second derivative with respect to x? So the part that is confusing is you have to realize that the second derivative, well, it's the derivative of the first derivative, right? So I mean, if I ask about the second derivative, so if you remember that notation, that is the derivative with respect to x of the first derivative, which is again a function of t, right? And then that means the same rule applies. So imagine you have basically another parametric curve, but instead of y, you have dy dx, the first derivative, as some function of t. So let's call that f of t. And again, x is also a function of t as before. I should write here maybe h of t so that we don't confuse it with the top of the page here. So the same rule applies, but by replacing y with dy dx. So once again, let's review the rule, right? If you look at the top of the page, we have y as a function of t, x as a function of t. So dy dx is simply the derivative of y with respect to t over the derivative of x with respect to t. Now, if I did compute the first derivative, now I have dy dx as a function of t and x a function of t. So if I want the second derivative, I apply again the same rule. So the second derivative is going to be again the derivative of the derivative with respect to t. So it's going to be d dt of whatever your answer was for dy dx over dx dt. So in this case, dy dx was, what was it, 1 plus 1 over 2t, and then dx dt was 2t again. So on the top, that's like 1 over 2 t to the negative 1, so minus 1 over 2 t squared over 2t. And if we simplify this, this becomes minus 1 over 4t to the power 3. So if I want to continue with the third derivative, we won't do it obviously, but if you want to continue, again, you're going to do the derivative with respect to t of this again over dx dt. So again, if I want, let's say, I want to compute it, but just to illustrate. So if I want the third derivative of y with respect to x, That's the derivative with respect to x of the second derivative, which I just computed. And then again, using exactly the same rule, that's the derivative with respect to t of the second derivative, again, just computed, over dx dt. So that's how you can continue on and on if you want higher order derivatives. So let's actually do another application. Let's do a tangent line, for instance. We're going to go over that a little bit on the second page. All right, so let's say we want to find the tangent line at the point 1, 3 to the curve given by the following parametric equations: x equals 1 plus natural log of t, and then y equals t squared plus 2. So obviously t is greater than 0 for the natural log to exist. Now, one thing to keep in mind here is the formula for the tangent line is the same, basically, but you have to make sure you don't confuse the point, which denotes the x and the y coordinate, right, of the point on the curve, with the corresponding value of the parameter. So it is still true that the tangent line, is the formula is going to be y minus y naught equals m times x minus x naught, right? The point slope form, where x naught, y naught is the point in question, 1, 3 in this case, and m is going to be given by the derivative dy dx at that point. Now that means, notice I need to figure out the parameter value at that point, because your derivative will be in terms of t. That's the whole point, right? So how do we do this if we work with parametric equations? So we start with the derivative using the formula from the previous page. So dy dx equals dy dt over dx dt. dy dt is 2t, and then dx dt is 1 over t, 0 plus 1 over t. So if I simplify this, that's going to be 2t squared. Okay, now what is the value of t at the point 1, 3? So to find the value of t, you go back to the parametric equations and set each x and y equal to the parameter values. Equal to 1 and 3. Right? So 1 plus ln of t is the x coordinate. That's going to be 1 at that point. T squared plus 2 equals 3 because y is 3 at that point. So notice that if you compute these correctly, if you solve for t correctly, it should be the same value of t for both. Because obviously for a given value of t, you obtain a point on the curve, right? So when you imagine you sketch this curve, and you have the point 1, 3, that should come from a precise value of t that you need to find right now, so you can plug it into the derivative. So in fact, you can solve only either of these two. You don't have to solve both, but typically you could solve both of them just to make sure you don't make a mistake, like a kind of like a checkup. And sometimes actually you need to, because for instance, in this case t is positive, so because for instance if you solve the second one, t squared is 1, so normally you say t equals plus minus 1, but you know already t is positive, because otherwise the natural log wouldn't be defined. And then it's just a simple matter of checking the first one, 1 plus ln of 1, that's 1 plus 0, and indeed is equal to 1. So both equations, when you set them up equal to the point in question, should give you the same parameter value. So dy dx at the parameter value t, sometimes if you want to be fancy, you can write it down like this. So I want dy dx at the parameter value t equals 1. That's 2 times 1 squared, which is equal to 2. So the slope at the point 1, 3 is 2, right? The derivative of the function at that point. So at this moment, of course, you use the point slope formula. So y minus 3 equals 2 times x minus 1, which gives you 2x minus 2, and if you add 3, that gives you 2x plus 1 as the equation of the tangent line. In some other problems, you are given the parameter value. So for example, I could have asked, here's another version of the same problem. What if I ask, find the equation of the tangent line at t equals, let's say e. That's going to be a more tedious answer because it contains e, but it's still fine. So in this case, I gave you the parameter value, but in that case, then you need to compute the x and y coordinates of that point. So it's kind of the opposite of the previous, right? Here you plug in the parameter value into the parametric equations. So 1 plus ln of e is actually 2, ln of e is 1. And then this will be e squared plus 2. So the point on the curve will have coordinates 2 and e squared plus 2. And then just like before, you're going to have to compute the derivative and plug in the parameter value into that derivative. We already know that dy dx is 2t squared. So dy dx at this parameter value is 2e squared. And so that's the slope. So if you are given the point, you solve for the parameter value. If you are given the parameter value, you plug it in into the parametric equation to actually find the point where the tangent is computed. So here the point slope form is y minus e squared plus 2 in parentheses. This is 2e squared x minus x naught, which is x minus 2. So let's just write it with everything on the other side. So 2x e squared times x minus 4e squared, and then if I move e squared plus 2 on the other side, I get 2e squared x minus 3e squared plus 2. All right, so the last topic for today as an application of calculus with parametric curves is the arc length. And the arc length formula is actually very similar. Well, it's a little bit different, but not that much from the usual one. And let me actually illustrate how that formula is established, and then on the next page we'll do an example. You might remember that when we computed the arc length, we actually we approximated the arc length, the curve, by a small piece of the curve. And that small piece of the curve we approximated by a straight line and put that straight line into a right triangle. And so, for example, this would essentially indicate, this side of the rectangle would indicate the change in the x coordinate, and this this side will be a change in the y coordinate. So basically, the arc length, which is sometimes denoted by ds, from Pythagorean theorem, essentially this is going to be square root of change in y squared plus change in x squared, dy squared plus dx squared. And when we have y as a function of x, for example, we could simply pull dx out, and that gives us the formula that you are familiar with, that you integrate, right? Square root of 1 plus dy dx squared, and then times dx. What we're going to do in this case is essentially pull out dt, because in this case it's neither y as a function of x nor x as a function of y, but each of them is a function of t. And the goal is to actually write the formula in terms of t, because we may have just the parametric equations. So in this case, then the arc length, so let's start again from this. If I divide and multiply by dt, so we're going to do basically kind of like algebra trick here. We're going to divide and multiply by dt squared inside the radical here. So we have dy dt squared plus dx dt squared. So that's dividing by dt squared and multiplying by dt squared inside the radical. And if I pull the dt out, then I have basically, and let's start with x just because it sounds better. So I have dx dt squared plus dy dt squared inside the radical with dt out. So that's essentially the piece that you integrate over the parameter domain. So let's say the curve is defined by two parametric equations. And let's say the parameter domain is AB. So in that case, the formula for the arc length will be the integral from A to B, square root of dx dt to the power 2 plus dy dt to the power 2 dt. So very similar, except that you square the derivatives with respect to t for both coordinates, x and t, x and y. So let's do an example on the second page, on the next page, and then I think that will be it for today. Okay, so let's find the arc length given by this parametric curve. X equals 2 plus 3t squared, y equals 5 plus 2t third. And it's actually an example so that we could integrate it easily, so it doesn't take too long. And the parameter domain is 0 and 1. So let's just write directly the formula. So the integral from 0 to 1, square root of dx dt squared plus dy dt squared dt. And let's see, dx dt will be 60. So that's to the power 2. And then dy dt is 6t squared, again to the power 2 from the formula. Right, so 60 for dx dt, 60 squared for dy dt, and then square both of them and add them together. This one will be 36t squared plus 36t to the power 4. This looks like a difficult problem, but actually it's not that bad once you pull out t squared out of the radical. Or let's actually pull 36t squared. So I can pull 36t squared, so I'm left with 1 plus t squared. And if I move that out of the radical, that's going to be 6t square root of 1 plus t squared dt. Okay, so notice that because we have t on the outside of the radical, so let's write it one more time here, and I can actually pull the 6 out. And put t together with dt just to see the substitution better, right? So because of that external t, it turns out that the u substitution would work. So you can take u to be 1 plus t squared, du is 2t dt. Let's change the bounds. So if t equals 0, u equals 1, and if t equals 1, u equals 2. And of course, du over 2 will be t dt. All right, so my integral now is 6, integral from 1 to 2, square root of u, and then du over 2. That's u to the 1/2, and then integrate that from 1 to 2. And that ends up in 2 times 2 to the 3/2 minus 2 times 1 to the 3/2. And that's 2 to the 5 over 2, 3 over 2 plus 1, minus 2. Okay, so that concludes this lesson. The last two lessons of the class will be related to polar coordinates. Just to anticipate a little bit, the idea is that instead of identifying a point on the plane by the x and the y coordinate, you're going to identify that point by its distance from the origin. So this segment is denoted by r, and by the angle measured counterclockwise with a positive semi-axis, x semi-axis. So this point is identified by two numbers, the so-called polar radius, the distance from the point to the origin, and the polar angle. You may wonder, so before I call it a day, because I have this room here of maneuver before I call it a day, on this page, you may wonder, why do we bother with things like that? Well, here's as a comparison, and try to appreciate the difference basically. Let's say you have a circle, right? A unit circle of radius 1. In Cartesian coordinates, the unit circle is described by the equation x squared plus y squared equals 1. With x between -1 and 1, if you want to view that as a function of x. And as a function of x, that's going to be plus minus 1 minus x squared. Obviously, that's harder to integrate. For example, if you have to integrate stuff related to this square root, it could be rather tedious. And in topics like partial differential equations could be really painful, in fact, if you have, for instance, conditions based on these type of expressions. In polar coordinates, so if you describe the point by polar coordinates, the equation of the circle is simply r equals 1 with that parameter, so theta becomes a parameter in this case, between 0 and 2 pi. So it's as simple as that. So clearly in polar coordinates, shapes like a circle or portions of a circle or something similar like that are much easier to describe with easier expressions. So with this cliffhanger, let's call it a day, and I'll see you next time.